So in the current video, we'll continue our discussion on the integration of rational functions, where the top and the bottom of the fraction inside the integral are polynomials. And the steps are actually quite standard. The step one is to compare the degree at the top and the bottom. And we focus on the case where the bottom has high degree. And the first step to do is to factorize the denominator completely. So these are all the things that are stated on this page. And actually, last class, we already finished a part of the discussion of case A. So this video will actually try to continue our discussion. So please look at the board now. And last class, we have actually finished the discussion for the category 1. And for this video, we'll look at the category 2. And the fact is that we have some degree 2 factors which cannot be reduced further in the current case. And now let's check out one example. So please look at the current case. Now the top you see has a lower degree than the bottom because the top has degree 2 and the bottom actually has degree 3. So we can continue our discussion now. So let's factorize the bottom. We have the factor x, which is a common factor of the both terms, multiplies to open bracket x squared plus 5, right? And these are basically the terms that you have for the denominator because you see you have one degree 1 factor and the second factor actually has degree 2 because you cannot break it down further. There's no real solution for x squared plus 5. And we can continue our discussion here by the use of the partial fraction decomposition. So you see now the fact is that we have to stick with something we learned in the last video. The fact is that whenever you have only two factors, there should be only two smaller pieces of fractions in the partial fraction decomposition. However, there's something we have to make a note about. Usually, when the denominator has degree 3, we must need three constants for this. So I'm saying the degree of the bottom, the denominator, is related to the number of constants we need in the partial fraction decompositions. And for the first factor is fine. For the degree 1 factor is always easy. We can just add a constant to the top. However, whenever you have degree 2 factors, you have to be careful because at the top, we actually need a degree 1 factor at the top. So now degree 1 means what? Degree 1 means something like maybe 7 plus 1, 2x minus 1, etc. Right? It means we have to make it look like bx plus c, right? And now algebraically you have to solve for the ABC. And let's just make a common denominator on the left and the right hand side first. So please look at the current formula we have on the right hand side. I make a common denominator. So now the common denominator is the same on the left and the right hand side. And let's focus on the right hand side. What I did was for the first term a, I multiplied it to the factor it doesn't have, which is x squared plus 5. And similarly, for the second factor, bx plus c, you need to multiply to the factor it doesn't have on the denominator, which is x, right? So that's why I multiply x to bx plus c. Now, it is your job to compare the numerator and find the ABC. So let's focus on the numerator together. The fact is that maybe by some clever choices of x, we can actually find some constants first. I think if I choose x 0, it's actually a good choice because you see when x is 0, the second term, this factor is 0, which means the second factor is simply 0, right? And because anything multiplied to 0 must be 0, so I'm saying the second term must be 0, and the first term on the right-hand side is going to be a times 0 squared plus 5. And for the left-hand side, when x is 0, I think we have only 10. So I think it means that 5a equals 10, which means a is actually 2. So 2 is the easiest to find because we just need to replace x by 0 and we can solve that. However, now if you look at the expression on the right hand side more carefully, b and c always come together as long as the choice of x you choose is non-zero. But we cannot choose 0 again, right? Because we have done it already and we got a from there. And it means what? It means for any non-zero value of x, you put it there. B and c always come together. So you cannot just eliminate one of them and to find the remaining constants. You cannot. A is found. A is found. So it means what? Algebraically, it means no matter which choice of x you choose now, you are always left with the equation with two constants. But the fact is that if you choose two different values of x, you'll get two equations in constant b and c. And two equations, two unknowns is a typical topic that you have seen in school. So let's do it together by choosing two different values of x. For example, I can choose x be 1. In that case, the left hand side is gonna be 16 equals, and a is 2, right? So I just put it here. And the second factor of the first term is gonna be 1 squared plus 5, and for the second term is gonna be 1 times b times 1 plus c, which is b plus c, right? B plus c. And now we can write down an equation in terms of b plus c on the left hand side. So I think the equation is gonna be this part is something like we have to pull the constant to the left hand side. So I think it's 16 minus 12, which is 4. And let's choose another value of x randomly. You are free to choose any value of x now, apart from 0 and 1. We just want another equation in terms of BC. So from there, we can solve the two equations to a known system. For example, I can choose maybe x be minus 1. So in that case, we'll have something like this on the left-hand side. And for the right-hand side, a is 2. So the second term in the first term is minus 1 squared plus 5 plus minus 1 open bracket b times minus 1 plus c. So I hope you see what I'm doing. And if you do the arithmetics carefully, you'll have the next equation. Please note that the second term on the right-hand side is minus 1 times b minus b plus c, which means I can write it as b minus c, right? So I want the second equation to be b minus c equals something. And after the calculation of this arithmetics, you can notice that b minus c is actually 2. And please look at the two equations you have, the first box and the second box. And you can eliminate one of them to solve for one constant first. Maybe I can add the two equations up. After adding the two equations, you see the left-hand side is b plus c plus b minus c. So the c is gone, and which means you have 2b. 2b is now the same as 6, which means b is actually 3. And to find c is actually easy because I can use the first equation. b now is 3, right? So is 3 plus c equals 4, which means c is actually 1. So at this stage, we successfully find all the constants a, b, c, right? And let's look at the integration problem now. So please look at what we have here. Originally, I was asking you the question same as the left-hand side. And after using the partial fraction decomposition, the first term you see, which has the factor x as the denominator, we found the a already, which is 2, and we found the b already, which is 3, and c is 1 actually. So we found it already, and now the remaining question is for you to do this integration. And the first term is clear because the first term is just the same as 2 times ln x, right? And the question is now about the second term. So I try to give you some hints. You see, the fact is that to resolve it, it is not straightforward, but the method is quite standard in the sense that you always have to split it into two different integral based on what you have on the numerator. The term that you have, the x term, should be separated from the second term, which you have only the constant term at the top. So I split it this way because the way to solve these two are completely different. For example, for the first term here, 3 doesn't matter. 3 you can pull it out, right? So essentially, I'm asking you to consider an integral of x over x squared plus 5. And I think this one can be solved by the use of substitution because, for example, if you let u x squared plus 5 and du is going to be derivative of x squared plus 5, which is 2x times dx. Now you see I'm doing that because if you look at the bottom of this fraction, which is u. How about the top? The top you actually have x times dx, which is the same as this. It means what? It means x times dx is actually the same as, we can pull the 2 to the left hand side, which means it's du over 2, which means you are essentially integrating 1 over u times du over 2. And I trust that you're able to do this calculation, right? Because, for example, 1 over 2 as a constant can be pulled out, and you're just integrating 1 over u, which is ln u, and u is actually the same as x squared 5, right? So basically, this answer in the green box is quite the same as this answer. Of course, we need to multiply this answer with 3. That's the constant we have. And basically, the way to solve this integral is done. How about the next one? The key fact is that the remaining one here, it does not have the x term with it. So we cannot use the u substitution anymore because the u substitution works because you have the x at the top and the x dx, if you consider them together, it can be absorbed by the du, right? So it's actually crucial to have the x term at the top. So it gives us a chance to use the u substitution. However, this case we don't have anything at the top, and but we have to make use of a fact. The fact is that please recall some formula. If you have something like x squared plus a in the bottom, if you try to integrate that, the formula is that it is related to inverse tan of x over square root of a, and trigonometric function needs to be multiplied to 1 over square root of a. So maybe you haven't seen it, but I believe that you must have seen this. So let me write this one down. This one is the same as inverse tan of x for the answer to the indefinite integral of 1 over x squared plus 1, right? And now you see these two answers are somehow quite similar, but the fact is that the kind of trigonometric substitution we need to make use of is x equals square root of a times tangent theta. You see, I'm doing this because of what? I'm doing this because x squared plus a now equals a times tangent square theta. This part is x squared plus a, right? And if you pull the common factor a out, you are having 1 plus tangent square theta inside the bracket, and this one is secant square theta. And also, from the first substitution here, usually you need to find x. Dx is what? Is square root of a secant square theta d theta. Secant square theta because you need to differentiate tangent theta. So it means that by the trigonometric substitution, you would notice the following. You're actually integrating an expression like this, and this one is actually what we have for the dx, and the bottom now is the same as this term, which is x squared plus a. Now you see, coincidentally, secant square theta is cancelled. So essentially, you're left with a constant, right? The constant you have is square root of a divided by a, which is 1 over square root of a. And you need to integrate 1 inside the integral. So it means the answer is 1 over square root of a times theta. And this is essentially the answer to this current integral. But you need to tell me the expression of theta in terms of x. The fact is that the theta is actually the same as inverse tan of x over square root of a. You can check all my calculations here in the bottom right corner. So it means the formula here is actually the same as 1 over square root of a times inverse tan of x over square root of a. Anyway, let's drop all of these. We only need this. We only need this for the formula at the top left corner. So let's come back to our current computation. This is the thing that we care about. We have to finish this calculation off. And you see, whenever you have a degree 2 factor term, it is not something easy because you need to split it into two different terms separately. For the left-hand side, which you have the x term. When you have the x term, it is slightly easier when we do the u substitution like this. Anyway, the answer for this term is done. It's quite similar to this. You need to multiply by the 3. And for the right hand side here, this box, we have to make use of this formula. So anyway, the answer, we'll write it down here. Anyway, the whole answer is that for this second term, it is the same as this box. It's 3 times half times ln of x squared plus 5. And the third term, which is the integral of this, I'll use this formula now. It is the same as 1 over square root of 5 times inverse tan of x over square root of 5. And that's the answer to this problem.